why do we talk about average kinetic energy? And there's a reason I put this graphic on here. We could think of these all as particles, right? Maybe this is a gas or a liquid. Why would we talk about the average? Just looking at this picture. If you look closely, you can see that some particles are moving slowly, right? And some of them are moving much more quickly, right? And when we are taking a temperature, we are not interacting with just one of these particles at a time. We're interacting with all of them, right? So the measurement we end up getting is a result of all of these, which is an average mathematically, right? If we're interacting with all of these things, we have to average out all their values. So that's why we say average kinetic energy and not total kinetic energy or something like that. Now, let's keep thinking about motion and kinetic energy. And now let's talk about the structure that's different between solids, liquids, and gases. So, got some nice pictures and graphics here. Um, let's say that these spheres could represent either atoms or ions or molecules, right? Some sort of large particle that's in these substances. Um, what do you notice about, let's start with a solid. We can see that the particles here are all bunched together, right? And they're in this nice repeating pattern. Call that a lattice. So solid particles are vibrating. You can see they're vibrating in fixed positions, right? With a fixed volume. We've kind of talked about this before. Everything has some amount of energy, and that means it has some amount of motion. And solids like to stay in these nice organized lattices, but they are still vibrating. And they're going to go in like every direction, right? A liquid, they're able to move more freely, but they are still close together. So it's difficult to compress a liquid, right? It can be done sometimes. If you put enough pressure on certain liquids, they'll turn into solids, right? But they take up a fixed amount of volume as well. That's why it's difficult to compress them. The gas particles are moving very randomly and freely, right? They have broken free from their bonds, and they have no fixed volume, right? And when we think about this, now that we know about kinetic energy, right, we want to think about this in relationship to kinetic energy and the forces that are attracting these molecules to each other, right? So here's our next question. How does kinetic molecular theory, the idea that the molecules are always moving, right, and that results in a temperature, explain the structure of matter? So think about that question. See if you can come up with an answer for it. So we can say that as that the reason particles are close together at low temperatures is because the interparticle forces of attraction are greater than the kinetic energy of the particles, right? So the forces, the electrostatic, electromagnetic forces that are attracting these things to each other, right, the positive and negative forces, are stronger than the average kinetic energy or the kinetic energy of a given molecule. So they're all vibrating, right? But they don't have enough energy to escape those strong magnetic electrostatic bonds. As you give them more energy, right, you increase the temperature, like in a liquid, they start to break free from some of those, right? They have enough energy that they can move past each other, but they're still attracted to each other enough that they won't break completely free. But if you give them enough energy, they will completely break free from each other and they will all fly around in random directions. So solid, liquid, gas. You can think about that in terms of energies and interparticle forces, right? We'll have special names for those eventually. like intermolecular forces. We'll start to name exactly what those are and what those mean, but right now you can just think of them as the attractive forces between particles. So here's kind of what I was talking about. Particles are close at low temperatures because of those forces. As the temperature and so the kinetic energy increases, those forces are less and less able to hold them together. And then in a liquid, the interparticle forces are able to hold particles close, but not in fixed positions. And then finally, the gas can break free, right? Which is what I was talking about in that last slide. So now let's think about, this is more like a knowledge of science question. What's the relationship between models? This would be like a model. Or making something to try and communicate something, and theories. We learned this first, and then we looked at this model to try and understand this better, right? So I want you to answer this question, to think about it. What's the relationship between models and theories? And there's not wrong answers. Just, what do you think? How are these things related or different, or how do they work together? And then I'll give you a few of my ideas. So I think of models as representations, right? Diagrams, graphs, formulas, in this case, these animations, right? Um, so they're representations of reality that provide a set of characteristics or properties for a system. So like these are systems of particles, and we're looking at their characteristics, how the, like in this case we're looking at how they're organized and their energies and their motion, right? And this is telling us something, modeling something. A theory is a proposed explanation for a phenomenon that uses one or more underlying models, right? So this theory is using models to help explain a phenomenon like temperature, right? It uses a model or more than one model to explain something else. Uh, so, with that in mind, let's do some practice questions. Which best describes water vapor? So we've got particle movement, volume, and relative strength of the interparticle forces. Take a second, look over your choices, and then write down what you think is the best answer. So best answer is D. Particle movement is random, right? We saw that in the gas. This is random movement. Water vapor is a gas. The volume is not fixed. It will fill up whatever space they're in. And the strength of the interparticle forces is negligible, right? All right, now I want you to draw a graph, make a prediction. In science, we make predictions and then we test. This is good practice. Predict the graph produced when a hot liquid is cooled below its freezing point. So up here, it's starting as a hot liquid. Oh, sorry. And then down here, it is becoming it's cooled below its freezing point, right? This is your temperature. This is time. So whatever you think this graph is going to look like, I want you to draw it in your notebook. So take a second and do that. So you might have seen the answer. I kind of clicked on it. I will say it's very common for students to draw just a straight line down. That is a totally reasonable prediction to make, because we're cooling down a hot liquid, so the temperature is getting lower, right, as the time goes. But what it actually ends up looking like is something like this. You can imagine each of the x's is us taking a data point, like we're taking the temperature, right? And the temperature is decreasing, and then we get this plateau here, and then it continues to decrease. So we have an initial slope, the hot particles are losing some of their energy, and then the plateau happens. I want you to think about why we get a plateau. This is when it is freezing, I will tell you, right? Hot liquid is freezing, now it is frozen, and the temperature begins to decrease again. Let's take a second to think about why that might happen. Why is there a plateau? Think about the things we've learned, the theories we've been talking about. I'm going to explain it in a second. I'm going to ask you another question first. So, I want you to see if you can pick out the right answer now. Which best explains the parts of the cooling curve we saw? So there's this, remember there's the sloping parts, which would be these, and there's the plateau part, which is this, right? So try and pick the best answer from these. Give you a moment, you might want to pause again. So the best answer is C. During the slope, particles lose kinetic energy as heat is transferred to the surroundings, right? So we have a hot liquid, we're cooling it down, maybe it's in an ice bath. So that heat is escaping into the ice, right? When we get to the plateau, the heat is transferred to the surroundings at the same rate as heat is produced within the substance by the formation of intermolecular forces. So the liquid is turning into a solid, right? It is forming those special lattice bonds for the formation of intermolecular forces. And that actually makes heat, right? So the ice is producing heat and it's also losing heat, but it's happening at the same exact rate. So now I want you to predict the heating curve of water from X, which is below 0 degrees Celsius, all the way up to 110 degrees Celsius. So somewhere up here. We'll draw this into your notebook. See if you can make a correct curve. I'll give you a second. So the correct curve looks about like this, right? We see these slopes again, and we see we now have two plateaus. Why do you think we have two plateaus? So as we think about what phases are happening, or what each of these parts are, the plateaus start to make sense, right? So we start with a solid, it's below 0. And then as we get to this first plateau, this is when it's melting, right? So it's taking in energy, and that energy is being used to break those lattice bonds, right? So instead of increasing the average kinetic energy of all the particles, that energy is getting used to break those lattice bonds so that it can then become a liquid, or it will begin to heat up again. The average kinetic energy increases. And then as it's boiling, the energy that's going into our liquid is being used to help those particles escape from the liquid, right? And become a gas. And so we have another plateau at 100, and then eventually we get a gas that is heating up. So this all has to do with energy, and these points, the average kinetic energy is increasing, and these points, that energy is being used to do something else, right? So got to think about energy when we look at these